Okay, for this problem, we're given an array of distinct integers called candidates and a target integer target. They want us to return a list of all of the unique combinations of candidates where the chosen numbers sum up to the target. So basically a 2D array, an array of arrays, where each array is one possible unique combination of candidates that sum to the target. Right. So the same number can be chosen from the candidates array an unlimited number of times. So say you're iterating through your candidates array 1, 2, 3, your target is 7. You can pick 1 up to 7 times, right? So one of the solutions would be 1, 1, 1, 1, 1. So that's what they mean by we can choose the same candidate unlimited number of times. And then our set of possible solutions also has to be unique, right? And they define uniqueness by 2 of the chosen numbers have to be, or at least one of the chosen numbers from 2 combinations have to be unique in the frequency which they occur in that combination, right? So the order that they are in doesn't matter as much. This is just it's a combination problem, right? As opposed to like permutation or something. The way we're going to solve this is we're going to do recursive backtracking with like a depth first search. And let's just get into that straight away. So, and I don't remember the example here. So 2, 3, 6, 7, and then target is 7. So okay, so that's our candidates array, and then our target is going to be equal to 7. Let me just double check that's right. Sweet. Cool, right? And then obviously these are the 2 answers, but algorithmically, let me just show how to get there, right? So we're going to seed our recursion with just like an empty set. This will be our combination that we're considering at any point in time. So backtracking basically enables us to, rather than create a million different arrays in memory for our, like we're going to have our solution just like over here. This is like our 2D array of arrays, right? Once we have found our array sums up to the target, we'll add it over here. But we don't want to create a million arrays to add to the solution. Like ultimately, we're going to have a million arrays in the solution, but we don't want to keep like for ones which might not even be a possible answer. We don't want to keep track of those in memory, right? That's going to be terrible. So backtracking allows us to have one array. We can keep forming the different combinations with one array. And if we see that the array for this combination, at a given point in time adds up to the target, then only at that point we'll take a snapshot of it and then add it to our solution, right? But otherwise we're just working with one array in memory. So sort of, there is a recursive component to this, but well, not sort of, yeah. There will literally only be one array in memory here. So anyways, yeah, let's just get into this. So we want to also have a index indicating where to start at in the recursive call stack, because each recursive call is going to need to loop over the remaining numbers, right, to ensure that we're maintaining like uniqueness. Yeah. So at first that'll just be, we'll call that I, it'll be 0. Okay. And then that's indicates an index in this array, right? So for the first thing that we'll do, we're basically going to check. Also, well, one more thing, actually, this is kind of important, so I don't want to leave this one out. We're going to have a variable that basically helps us with the sum. So one, you could do this by literally passing the sum in at every point. Because remember, like we would create even worse time complexity than we would need if we had to like recompute the sum at each point in the recursion. So what we want to do is just save the sum as just an integer, right? That way we only have to add the numbers once. What I'll do is I'll actually do the inverse of that. So we can, every time we add a number, we can subtract it from just some dummy variable, which is the same as target. And that'll be the sum. Once we try to subtract a number and this goes negative, we know our sum is like exceeding the target. So that's just like the inverse way of doing that. I find the code a little cleaner, so we'll do it that way. Right now, that will be 7, right, when we're seeding the recursion. So enough with the first node here in the tree. Let's start doing the algorithm. So we're first going to check, okay, is our target number here equal to 0? If it is, then we can add to the solution. It's not great, so we want to continue trying to add other candidates, right, to try and get to the target. So the first candidate we're going to add here is going to be the 1. I will still be 0 because we need to be able to pick this candidate again, right? So I will still be 0, but the this number here will be 5, right? Just to keep track of that sum, sort of, right? I mean, that is exactly what we're doing. So, okay, and we actually wouldn't go this way. This is like a depth first search. So before we do any backtracking this way, the algorithm will basically check, well, it's going to do another call. Right, we're going to pick the 2 again. So, but 2 is already in the array, so we're really just, we're adding it again. Let's see, I is going to be equal to 0 still, and then this is going to be, -2, so, because that's the number we just added. So now it will be 3. And then same thing again. So let's do that. I is going to be equal to 0 still, and then this is going to be equal to 1. We'll try to add another 2 again. Notice how we're getting pretty close to the limit here. And actually what happens is we're not even going to allow this call to happen. So if, this candidate we're trying to add minus our target is less than 0, right? If it's negative, then we're just not even going to do that. So at this point, we'd be done with this path in the call stack. We would do backtracking on this level and add the next candidate, right? So next candidate's going to be 3. But with the same array, right? So we're passing the same array because we're using the same one in memory. We're going to add the 3 because that is less than 7. And in fact, when we get to this array, we're going to find that that is a possible solution, right? So I is going to now be equal to 1 because we're now at the 3 for this portion, for this path, I guess, for the rest of this path. So this is going to be 0. That's what we're looking for. So this is a solution which will get added over here. So let's add that one. And this might take a little bit longer to walk through this problem, but I think it's probably worth it just for understanding. This one is a little more complicated. So we're done at this point. Once we've found an answer, we're not going to keep making calls. There's no point, right? Because we would just the sum would be bigger. It would be too big, right? So we'll do backtracking. And we would try to add, let's see, that's like going through that. to just keep this on the same level visually. So like we would try to add the next number, which is the 6. But obviously 6 or 3 minus 6, right? That's going to be -3. That's negative. So this call wouldn't happen. And then, similarly for the 7, that call is not going to happen. So we would be then done with this path. We would do backtracking to add the next element on this level, which is we already did we tried with 2. It would be the 3. So we're going to try to add this 3. Again, we're back to this or state of the array state, which is it's literally the same array in memory. We've just been removing the elements before we try the next paths. So I would be 1 here, just to say we're now at this 3 candidate. And then let's see, 5 minus 3 would be 2. Okay, and then there's probably some more paths to check down here. Well, actually, no, because this is 5. 6 minus 2 is, or 2 minus 6 is going to be negative, and then 2 minus 7 is going to be also negative. So there's like 2 things we would try to do there. And actually 3 things, right? Because we would choose a 3 again, right? And 2 plus 3 plus 3 is 8, which is greater than 7, right? Like, in other words, we tried to add the 3, 2 minus 3 is negative, right? That's what the algorithm would have done. So all of these don't happen. We would similarly, we would go this way and add the 6 and then do like the same thing, as you can imagine. I won't actually do that out because it's obviously not going to lead anywhere. We've seen the solution. So this would have, let's see, the root node is going to have 4 children because of the 4 different candidates, which are less than the target, right? Or equal to, right? So we would add the 3 when we do that. So like that would be after we backtrack up from all of these, right? And then I'll do that just to show that it kind of keeps going. But at this level, right, our I is going to be 1, and that number for the running sum will be 4. And then similarly, right, we have something here for the 6, and then for the other answer, right, we would have backtracked up from these paths, and I'll just like X out of all of those. We're done with this, and then we're at this one, right? This is like the last one. I would be 3, and then this would be 0, which indicates it belongs in our solution set. So yeah, that's pretty much the algorithm. That took a while, but that's fine. This one, there's a lot to explain. So let's go over the time and the space complexity before we do the coding. So this in and of itself needs like a whole lecture, but for the time complexity, we're going to have basically, we have to look at every node in this tree, right? So the question we want to ask ourselves, I think, to, imagine the time complexity for this is like, okay, how many nodes are in this tree, right? Can we come up with a formula or an expression which is the number of nodes in this tree? Because when you think about it, all we're doing for this algorithm is we're visiting every node in this particular tree, right? So if we can figure out the size of this, or the number of nodes, then we can figure out the time complexity. And luckily, there's a formula. It's basically going to be at the base, we're going to have the number of the highest possible like branching factor of our tree, right? So that would be like the base. So the branching factor is going to be the number of candidates. So we'll say number of candidates is n, right? And then so that's the branching factor. And then the exponent here is going to be the height of the tree. And what is the height of this tree? Well, we can see that it does have some kind of bound, and it's basically going to be, let me have some other variables here because this is like kind of a big formula. We need to divide the basically the number of, we need to divide the target. So we'll say t equals target. I guess we already knew that because I was keeping track of it with t over here. But so we'll say t equals target, and then we'll say c min is like the minimum number of or like the minimum number among all of the candidates. So we'll say min of all of that. I don't know. I mean, that hopefully that makes sense. It doesn't yet. I know it doesn't yet. So for this time complexity, it's going to be t over c min, right, as the exponent. And then y, just because this is the formula for the number of nodes in a tree, right, from like discrete math. So, and then if you want to understand like even deeper why, that can, maybe you can look that up separately. But this is basically going to be the time complexity because this is in basically the number of nodes in this tree, and we know we have to visit each of those nodes, right, like at least once. So once again, n, where n is the number of candidates, right, in the candidates array, it's going to be n to the t into the target divided by the minimum candidate, right? And then just to kind of like show how that works, right? Like if you notice, how many levels are there to this tree? Well, if you say this is like level 1, level 2, depth 3, or depth, right? This is depth 1, depth 2, depth 3, depth 4, right? That like aligns perfectly. We're basically saying target, which is 7, divided by the minimum candidate, which is 2. So that would be like, what? I think like 3 point, yeah, 3.5. So like maybe this is some base function as well, but this is like approximately correct, right? So we'll leave it at that. And then the space complexity is going to be the height of the tree, right? Because at any point in this algorithm, we're going to be needing to maintain a recursive call stack in memory, which is exactly correspondent to the height of the tree, right? So say we were at this depth 4 here, at this recursive call, we would have, at least this call in memory, we'd have this call in memory, we'd have this call in memory, and we'd have this call in memory, right? So that's just going to be the height of the tree. The height of a binary tree is log base the branching factor. So we set our branching factor as the number of candidates in. So it's log base branching factor, and then the number of nodes in the tree, which we know is this n t over the minimum candidate, right? I can't even like do that because it's so small, but basically I just wanted to show before I write it that this will cancel out, and then it's literally just going to be the exponent. So it'll be big O of t over c min. That's the space complexity. And the space complexity is just the height of this tree, right? And then the tree itself is like the time complexity. So yeah, I think that's like the easiest way to think about this. Okay, so now that we've had like a whole discrete math course, let's finally start coding. So the way I'm going to do this, let's overload the combination sum method. It won't return anything. It's just going to modify some things in place. So it's going to take candidates and target, and we're actually just going to subtract from target as we go, kind of how I explained. We're going to need a vector, which is the current combo that we're on. And I don't know why I wrote combo for the type, but it's vector of integers. We'll call it combo. It'll just be empty. We also want the 2D array. So a vector of integers. We'll call this all combos. And then what else? We also want this might be it, right? We just basically want to seed our recursion. So we'll see if I think of anything else we're missing. And this actually, I was trying to overload this function, so this should be the same. We just want to call combination sum on candidates, target, combo, and all combos. And then I don't think I'm missing anything else. Actually, we want an extra. We want to keep track of where we are, right? So we can ensure uniqueness. So we need an iterator too. And then we can just return all combos at the very end of this. So let's finish the function signature of this guy. That's actually too much for one line, so let's fix that. And then very important also that these are by reference. We do not want to make copies of these. We're going to use backtracking to keep that space complexity down. And that iterator, which we'll just say is I. Okay. Let's now code this. Doesn't like my indentation preference, but it's going to have to live with it. So the first thing we're going to do is check if our target has reached 0. So to basically check if the current combo, which we're considering, sums up to our target. So if target is 0, then we at this point can add combo to all combos by saying all combos dot push back combo. And then we don't want to search anymore, because if we continue turn all if we don't want to continue searching, because we're going to exceed our right. I don't know why this is tripping me up. We're going to exceed our target, right, with the sum that is in the current combination. So once we have found a combination that sums up to our target, we're done with that path, right? That's it. Okay, so otherwise, we want to try and add all of the potential candidates which are still eligible, which we already haven't exhausted, right? So we're going to use the iterator to, that's where we're going to be starting. We'll say for int j equals I, while j is less than candidates, right? So we're just iterating through the candidates. And then j++. And then, so at this point, we want to add the candidate, right, to the combo. So we'll say, no, but we don't want to do that if target goes negative, right? So that means our sum of this combination is already, it would become too big once we've added it, right? So we don't want to add it. So we'll say if target or let's do if target minus candidates j, if that goes lower than 0, then at this point we know it is illegal to do anything, right? So I was actually about to say that it's the inverse of this, which we want to check to enable, to check if we are enabled to continue searching, right? So at this point, okay, it's totally legal. It's either going to be equal or we're still going to be able to add candidates to this combo in the future, right? So we can say combo.push back on, let's see, it's going to be candidates j. Okay, and then we're going to do recursion. So I'm literally just going to copy this thing, right? It's all of the same variables. We're passing candidates, we're passing target, which is we do have to update the target because we just pushed a candidate to it, right? So we're using that to keep track of the sum. So we're going to say target minus candidates j. And then we also want to make this equal to the index that we're on so that we ensure uniqueness. So we're going to make this j. And we're not going to do j plus 1 because we want to be able to reuse the candidate, right? So the candidate we just added, we say we might have to add it again, right? Multiple times. So we're going to pass that back as in as the index, as opposed to like skipping over and saying, okay, do the next one. Like we're going to do the one we're on again. And then the final thing for this is like the backtracking. So, once we're done with that path, we're basically going to remove the element which we just added. And then the next iteration will do all of the other ones, right? So, but this is the key here for the backtracking, right? It's like just erasing what we just did in the current call for when the parent call does like the next thing. So yeah, hopefully that makes sense. That's about it for this problem. If we can not code any bugs. So what's the bug for this? It's because J doesn't have a type. Yeah. Okay. Yeah. So hopefully this helps. If it does, getting throttled here. If it does, leave a like, and I'll see you guys in the next one. This was a super long video. Leave a super like if you're here to the end. See you guys. Peace.